Yay, physics in the summer. We are going to talk. Can you read that? B. Can
Yep.
you? Can you see it?
Yeah.
O-U-L-L-I. Bernoulli. The joke I use is that guy blows. Because it's all about fluids that are in motion. So, Bernoulli's principle. What it's based on is conservation of energy. All right, conservation of energy. What I want to remind you of from that, from your Physics 1 class is, let's pretend in our headsies this is some sort of incline that you, are going to slide down. All right? Up here, you have some potential energy, right? PE, which is mgh. All right, down here, you will have some kinetic energy, which is 1/2 mv squared. And if there's no friction, then the potential at the top is equal to the kinetic at the bottom, right?
Left.
Correct. If there is some friction, then there could be work done, and work is equal to force times distance. Okay? So all of that, remember, work then is what will cause kinetic energy to change, being different from potential. So if this work is done, it will change the amount of energy in some sort of system, right? Huh? So, in conservation of energy, then work causes changes in potential and changes in kinetic. All right? Well, that's called work energy theorems. That's not necessarily conservation. It just means work causes changes in energy. All right? Now, in the case of fluids, what we'll do is change it from mechanical formulas like you played with last year and get them more specific to when fluids are flowing. All right? So what I'd like you to envision now is, instead of this being a slide, what if it's a pipe with fluid flowing in it, a pipe with water, and that water starts flowing through the pipe? Then we can say, well, gosh, if there's no changes in diameter of the pipe, if there's no friction, if there's no anything, then the amount of water flowing in this area has a constant flow rate through here, and as it goes through the pipe, nothing much really changes unless the diameter of the pipe changes. Okay? And so that's what I'm going to draw next, is what happens if we have a pipe with diameter that changes. Okay? And I may go over there to do that. So what if we have a pipe with a diameter that changes? That could be something like that, where it's skinny up here and it's fatter down here. All right? And what we're going to do is keep track of a certain quantity of water that's flowing through that pipe. And if we can start down here or up there, it doesn't matter. But if we talk about the amount of water that's occupying this location here, and maybe it's flowing that way, going uphill, it doesn't matter if it goes up or down. Okay? But this amount of water can be described with a whole bunch of different letters. One of them is the amount of area that that pipe takes up. So area meaning the surface area of the opening of that pipe. So this I will call A1. Excellent for grill outs. Another one I will use is the length of this particular quantity of water, which I will call L1. So the area and the length of that, which again, I'm sure you remember, area times length could be a volume. The speed that the water is flowing, I will call a lowercase v. 1. So the velocity of this water as it goes that way in that location is called a lowercase v. All of this exerts or has some amount of pressure at one location. So there's pressure, area, velocity, length, and another one that sometimes becomes an issue, sometimes it doesn't, is how high up this center is relative to some ground point, which would be an H. How high up it is, like as an MGH, that could be an H1. All right, can you see the green? I can't tell. Can you?
Very lightly.
Very lightly, all right. Well, we'll go a little more green. Physics in the summer, Spence, huh?
The security guard in here wanted to know if it was okay if this student drew on the sidewalk out here.
Oh, if the student drew on the sidewalk, I don't know. Is it okay if I do this?
I think you're good.
Does it make you feel young?
It does make me feel young.
That's nice. You have a good assortment of colors there.
Well, this is what, it's summertime physics, which is, what we're all looking forward to is physics in the summer, right? I can't wait. Poolside physics, that's why they're all paying attention.
Bye, leader.
All right. So what letters? I'm sorry. So the letters we have again, the amount of pressure at this location, the area of this location, the velocity at this location, the length of that quantity of water, how high up it is.
No,
okay?
it needs to focus in again. It's like
Try like blocking out.
unfocused.
Yeah.
It's all right. It'll get
There
Oh, there we
we
go.
go.
There we go. We're back.
Cool.
We're back.
All right. Now, if I follow this exact same quantity of water as it flows through the pipe, since the pipe got skinnier, less area, can you see that length is going to have to increase? So that same quantity of water up here might end up looking like that. Thinner, but fatter. Yeah, and people think this class is hard. It's thinner, but fatter. My gosh. All right, so up here I have an A2. I have what, an L2, a different length, which is again the length that that quantity of water takes up. We have a different velocity. Can you tell if it's going to go faster or slower or stay the same?
Faster.
It gets skinnier, it goes faster. Yeah, that's why I remember you squish the end of a garden hose, it goes faster, right? So this is an increase in velocity here. That length, what else, what other letters? We had a height and a pressure. So there's still an amount of pressure at location 2, and there is a height from some reference point, H, a height 2, an H2. Oh, all right. And I think that's it. That's all of them. Okay, so as this water flows and we say, hey, energy is going to stay conserved, to remind you of what we did over there, we said, hey, work is what will cause changes in energy. There's 2 types of energy, potential and the change in kinetic. All right? Remember, work is a force times a distance. In your mechanics formula or your mechanics class last year, you said force times distance. All right? In terms of this particular situation for a Bernoulli, what we're not going to use is the letter D. We're going to use the letter L, which is the length of this red section here. So I'm going to replace that letter D with the letter L. So that force times, that was in purple, L1. Okay? Then over here, a potential energy, which potential you know is mgh, right?
Yep.
What I can do is call it an H1 or a Y1, I guess it doesn't matter. H1, H2, if you want to use it down here, I can still go mg, and I'll use an H in green, so that would be the same. Sorry, not a big deal. And then kinetic is 1/2 mv squared, right? is what your teacher last year called it. All right, now, again, instead of using the letter M, since we're dealing with fluids, do you remember how we can spell the letter M in terms of a density formula?
Rho V or something?
Yeah. Density is mass divided by volume, so instead of M, I can use rho times V. So this will become 1/2 density of the fluid. Capital V is volume of the fluid. This V I should have drawn lowercase or a cursive. The little cursive V is a velocity squared. All right, does that make sense?
V1, right?
Oh yeah, V, any of the given V's, sorry. Yeah, you're right. The 1 and the 1. Yep, cool. All right, now, can you see I can do the same thing with this M as I did with that M?
Yeah.
So instead of calling it an M, I can call it a rho V. So this is going to do the same thing. It'll be a rho times density times volume times G times that same H. Okay? Also, length. If I want to replace it in terms of something that has a volume in it, because you see this V and this V, both of those have V's, I can simplify this and turn this force times length. If I take the volume and divide it by the area, that's the same thing as a length. So the same thing as a length is a volume times an area. So this could be a force. Multiply that by a volume divided by an area. Okay? So that then is equal to the rho VGH plus the 1/2 rho V for volume, little v for velocity squared, okay? All right, now, here's where we say I will do my least favorite thing in the world.
Kill the V.
Kill the V's, my least favorite thing in the world, because there's a V here, and a V here. So if you divide everything by volume, that kills the volumes, and what you're left with is a force divided by an area. That should sound strikingly familiar, because force divided by area is pressure. So over here, I will have a pressure. Then over here, I will have what? I will have rho GH, where this could be the work, this is potential, this is kinetic, 1/2 rho V squared. Make sense? Okay? And up here in our initial drawing, the pressure difference between 1 and 2 is a change in pressure. That's like a difference in forces. When we do some work and we change the amount of pressure, what's going to happen is changes in pressure will cause energies to change. So a delta P will be a change in this plus a change in that. And this is the formula that is Bernoulli's principle, all right? All those changes. And do you remember, change of anything is always final minus initial, right? The change in anything is always a final minus initial. So it doesn't matter if you start at the top or the bottom. But what we'll end up saying is, what it'll end up looking like is, you can call it changes, you can move them over and call it all the same. But this would be what? A PF minus a PI is the same thing as a rho GHF minus HI.
Yeah.
And that's if you factor it out like that. And then we will add a 1/2 rho
VF minus VI squared.
VF squared minus VI squared. Cool? Simple?
Very.
All right, but it's just based on conservation of energy, fluids flowing through pipes, whatever, and then this is the Bernoulli equation is what we'll call this. Sometimes we expand it out, we move the 1s and 2s over. You can say sum of the energy at any one location. Do you remember that? How to say that? The sum of the energy at one location is the same as the sum of the energy at any two location, right?
Right.
So then the three types of energy, if we rearrange this, we got a pressure 1 plus a rho GH1 plus a 1/2 rho V squared. 1 is exactly the same as
the same thing.
P2, yeah, P2 plus a rho GH2 and a 1/2 rho V2 squared. Okay, this is the formula I want you to remember when we talk about fluids that are in motion. That's what makes it different from the past few things where the fluids were static. It was just like a swimming pool and nothing was moving. But this is why I make the joke, the Bernoulli guy, he blows. What that means is the fluids are in motion, and this is the formula. And then I'll make a video here in a bit which would be how to apply this math to Pacific problems. But yay, physics in the summertime, huh?
Yay. Yay, physics.
Cool.